Hello, this is the third video of our module on relations in the Discrete Math Review for Foundations of Computer Science. This whole video will be about equivalence relations. The first question that we want to answer about equivalence relations is, when is a relation an equivalence relation? We say a relation is an equivalence relation if it is reflexive, symmetric, and transitive. So since we defined all those things, I think it is now fairly easy to say what an equivalence relation is. So that's a definition, but again, we want to look at some examples to help us understand what an equivalence relation, what its significance really is, what it is qualitatively, and why it's interesting, right? So the first example, very simple example, is the relation xy, where x is equal to y. So in this case, we're actually just talking about equality, right? And we just want to check that all three properties are there and understand, how they are related here. So first, for any element x in any set, right? We certainly the case that x is equal to itself, right? So for anything we picked, then x is in the relation, right? So that is defined this way. And so therefore, equality is certainly reflexive. So the next thing we would check is symmetric. Well, if I find I have two elements in some set, and let's call them x and y, and I find that they are equal to each other, x equals y, then it's certainly also going to be the case that y is equal to x, right? So again, that's true. Symmetry holds. And then the third one, if I have three elements x, y, and z, and I find that x is equal to y, and I find that y is equal to z, it's clearly the case that x is also equal to z. This is something you've probably done so many times that you forget to think about it, right? But so this means that equality is an equivalence relation. And another way of thinking of that is an equivalence relation in some sense defines what we mean by equality. All right, now on to the next example. Let's say we have a relation where we say x and y are related if x and y begin with the same character. So here we're clearly thinking about a set of strings that we're taking a relation on. Right? And so let's just make up an example set that we might be thinking of. Right? Say this set contains the strings all, ball, at, and bat, and we'll say also bit. Right? So that's my set. Okay. So what I want to show here is, all right, is this an equivalence relation? How would I show it? Well, first I would go through and prove each of these three properties hold, right? Now, I'm not going to prove them here. I'm going to just kind of look at them and say, well, yeah, that's true. And we look at just take it as an example to establish first this intuition, right? So is it the case that this is going to be a reflexive relation? Well, if I look at the strings in it and I say, okay, what's related? Well, if they begin with the same character, all, the question I have to ask myself is all related to all? Well, that's a kind of a weird question, but what I'm asking is, does all begin with the same character as all? And the answer is yes, clearly. They both begin with A, right? And you can see kind of right away, get this sense that, well, that's going to definitely be true for every string in this set, right? So this is definitely going to be reflexive. Okay, great. So now can I convince myself that this relation should also be symmetric, at least, on this little example that I made up? And by the way, I'm being a little bit loose here. I should really, when I give you a relation, I should tell you what the set is that it's a relation on. And in this case, we're sort of implying, okay, that you probably know that we're talking about x, y, it's maybe it's the natural numbers or the integer or something where it would be reasonable. But, if we did this formally, I would have to say what the set is. All right, so, and in this case, we're just imagining a set of strings, right? So, all right, is this symmetric? Let's look at the example. What does it mean to ask if it's symmetric? The first thing is, it says, well, if x is related to y in this set, then the question is y also related to x? So I'll just take an example. If all is related to at, then can I also say, do I also expect that at is going to be related to all? And to break that down a little further, what I'm saying is if these two strings have the same first character, then can I reverse them in the tuple, and will that also be true, right? Well, yeah, it's true because reversing them doesn't change the first character. So I think it's pretty straightforward to say, okay, that's probably also going to be symmetric, right? All right, so what about transitive? Well, if I have a string, let's take ball, and I say I found that ball is related to bat because they both have the same first character, and bat is related to bit, and just intuitively, yeah, I can conclude it's pretty likely that ball is also going to be related to bit. And I mean, actually, it's certainly true that ball is related to bit, so I've shown this for one, but I think the intuition is that's going to be true for whatever string that I have in my set, right? All right, so that's the example, but a reasonable thing to say would be like, okay, well, you gave me one example, but that's not really great as far as a proof, right? How do I prove this is the case in general, assuming that we've defined some alphabet and we're talking about like the clean closure of that alphabet and we want to get every string in it or something like that, right? Okay, we can do that by adopting a slightly more formal approach in which instead of this example, I use symbols, right? So what I'm going to do is I need to figure out a way of writing what it means that the two strings begin with the same character. So I have two strings, x and y. And if they are related, it means they begin with the same character. This is kind of the opposite problem, what we had when we looked at R-pre, where I gave you the formalization and we really had to figure out what the sort of English phrasing was. But here, to write that these things begin with the same character, one way I can do that is I say x, assuming x, let's just assume for now that x, it has a character in it, right? In other words, it has a length of at least 1, right? And we'll deal with the other case in a minute where maybe it doesn't even have a character in it at all. But for right now, let's assume it has a length of at least 1. Then we could write it as C concatenated with some other string we'll call W, right? And I'm saying here now C, the length of C is equal to 1. This is some string that's only one thing long, so it's a character, and it will be the first character in X. W is any other kind of string, including possibly the empty string, if it is the case that X is only one character long. All right, so I can rewrite this. X, as long as X is at least one character long, I can write it this way. And I can do the same thing with Y, but I don't necessarily know that X and Y are the same, right? In fact, they're in general, they are not. So I just use some different characters or different variables to express this. We'll say du, right? And here also we're going to say the length of D is equal to 1, indicating that D is supposed to be the first character of Y and C is supposed to be the first character of X. Okay, so now that I've expressed them this way, all I've done is just kind of rewritten them as the concatenation of some other set of variables that I've given a few rules about what they are. Now I can say something about what it means when I have X is related to Y, right? If X is related to Y, what I'm saying is that my rewrite of X, CW, and my rewrite of Y, DU, tells us that C is equal to D, right? These two things have to be the same, right? And that means that these strings are related in general without having any idea what the strings are, right? All right, so now I can go through and check my properties. Okay, great. So if X is CW, then is CW related to CW in general? Yes, because C is equal to C in general. So this is just sort of the same as what we saw in the previous example, right? It follows from the equality of the character with itself. So great. Now we have a double check on reflexive, right? Reflexive is now proven in general. All right, well, if we have CW, if we have X and Y related to DU, and therefore that C is equal to D, is it automatically the case that DU is related to CW? This is asking the question of, is this symmetric in general? Yes, because if C is equal to D, then D is equal to C. And so this relation, both these strings also begin with the same character. So this is definitely symmetric in general. So we can check that off, right? And then if we have strings, this one's get a little bit more notation, right? If X is equal to CW and Y is equal to DU, and let's also have like Z, I guess we'll make that equal to F V. Hopefully there's no overlap there. Okay, so FV, right? And we've now said X is related to Y and Y is related to Z. And we want to know, does that mean X is related to Z in general, right? This is what we're trying to show. Okay, well, if we just have this first information here, can we get to here? Let's just do the normal substitution process. And we'll say we have CW is related to DU. That's my rewrite of XY. And DU is related to FV. That's my rewrite of YZ. Okay, so this means that C is equal to D, right? And this statement here means D is equal to F, right? And so this question of, does that mean X is related to Z, we can, using our rewrite, say that, what we're asking is CW related to FV? And that would be true if C is equal to F, right? But C is definitely equal to F because C is equal to D and D is equal to F. And we know equality already is transitive, okay? So that is also true, and we get, we've now proven this sort of formally in a general case, at least, with some reasonable precision. Now, if you're keeping me honest here, you should say, well, what about that case that you said at the beginning where your string is not length at least 1? What if it's length 0, right? Which is the same as saying, what if one of these strings we're talking about is the empty string? Okay, so let's talk about that. If one of the strings is the empty string and it's related to some other string, if we have this pair, right, we want to know whether this is in the relation. We have the empty string and some other string that is not the empty string. Can these be related? Well, the definition is they begin with the same character. There are no characters in the empty string. There are characters in this other thing. So they do not, right? So this cannot be in the relation. And so that's fine when we're looking at symmetry, because it means there is no pair XY where either X is empty or Y is empty. And so we don't have to worry about whether YX is in it, right? And likewise with transitivity, same issue, right? Since we can't form this pair, then we don't have to worry. So we can't form XY and YZ if any of these things are the empty string, then we don't have to worry about whether or not it's the case that X is related to Z in that case also, right? In both of those cases, the reason we're fine is that we're dealing with a definition that is essentially an implication, and we've proven that it starts with a false, that the antecedent can never be true, and so the implication therefore always holds. So that's okay in that case, right? But we do still have to deal with reflexive. And usually reflexive is the easy one, but here, remember, reflexive is a little different. It has to apply to every single element in the set in order for this relation to be reflexive. All right, so we have to answer the question, is the empty string related to itself? And if it's not, it's going to be a big problem for us. It's going to break the whole thing. This will no longer be an equivalence relation just because of that one missing piece, right? That little corner case that we missed. So we need to convince ourselves that this is true. And unfortunately, in this case, our informal definition isn't doing us any favors, right? We've said these things are related if they begin with the same character. That seems to suggest that if they don't begin with any characters, then maybe they can't be related, right? So I think because we were trying to define an equivalence relation, we probably want to rewrite this a little bit and say, something more like if x begins with c and y begins with d, where the length of c is equal to length of d is equal to 1, then C is equal to D. In other words, if we wrote this definition in this slightly more complicated but also a little bit more precise way, then we could say for sure that epsilon is related to epsilon because this entire antecedent is false and therefore the implication is true, right? And then we could say for sure that we've covered all of our cases and now we are definitely talking about an equivalence relation. Is definitely down in the weeds a bit, but it's worth saying, I think, because it gives you just a sense that sometimes these little details make a difference, right? And if you've done any kind of extensive programming, you've had any experience with programming, I hope you can see there's kind of an analogy to the kind of logical thinking that's required when you write a program, that these little corner cases sometimes can bite you, and you really have to practice reasoning in a way that accounts for them. Okay, so we have two more examples that I won't go into in nearly as much depth, but I just want you to have them in case you want something to practice with, right? Another equivalence relation we could look at is x and y, where they both contain the same substring. And another one that we brought up already is RL. Remember, this is the one where two strings have the same length. Given this definition of equivalence relation, we can now go on to define an equivalence class. And an equivalence class is a set. So let me walk through the definition, special kind of set that is related to this equivalence relation. So if we have some equivalence relation E defined on a set S, so we're thinking of a homogeneous relation here. Then we say for any element X in the set S, we can define an equivalence class of that element X. And that equivalence class is going to be the set of all the elements in S that are related to X under the relation E. But to illustrate this, let's draw a picture. We have our set S, right? That's the big set that we're talking about here. And there's going to be, here's our elements that are in S. Just kind of write a bunch of elements in random places here, and we'll say this element is called element X, and here's element Y. Let's say X is related to Y under this equivalence relation. Well, I know that equivalence relations are symmetric, so that means also Y is related back to X. And what I'm saying here is that if that is true, then X and Y are in the same class, the same subset. And in fact, if I discover Y is related to some other element, let's say Z over here, I can say if Y is related to Z, I can conclude Z is related back to Y, but also by the transitive property, Z must be related to X, and then by symmetry, X is related back to Z. So all of these are related to each other, and of course, because it's because it's reflexive, they're all also related to themselves. So we have this kind of completely connected graph that occurs here, right? It's a big group, right? And the idea of an equivalence relation or equivalence class, is that you're either kind of in this group or you're not. Everything that's related is part of this completely connected graph, and we can kind of sort of wall it off here from the rest of the elements, right? And we could say, okay, if this other element here, let's just pick this other arbitrary element, you say it's not related to anything. Well, in that case, it is at least related to itself because it's a reflexive, so it sort of stays in its own class. But anything that is related to some other element is going to form a class with those elements. So you kind of maybe just draw this quickly. Say these things are all related. You can fill in your arrows yourself, right? And everything, it's going to become part of some class or it's going to be in its own class, right? This is kind of what an equivalence relation does to a set. It creates these various classes. Now, of course, we have to talk about how we write these things, so we'll take a little bit of a notational interlude and say, okay, the way we write this is the equivalence class of X is written by this bracket around X, and we can add the subscript E to specify which equivalence relation we're talking about. If I don't say what E is, and this doesn't really tell you much, right? But assuming I've defined E, then this will say we have an equivalence class with respect to this equivalence relation. That's useful if you're talking about multiple equivalence relations kind of at the same time. But if it's obvious what equivalence relation you mean, like say, just equality, or you've already defined this, then we can just write X in brackets and everyone will understand that we mean the equivalence class with respect to this assumed equivalence relation. The way we write this symbolically as a set comprehension is that the equivalence class of X is all elements Y in S such that X is related to Y under the relation E, or the pair XY is in the equivalence relation E. Having established that definition, we can now immediately introduce a theorem, and the theorem is S is the union of its equivalence classes, right? So remember, S is this set that we define the relation on in the first place, and we're saying that if we take all the equivalence classes that are formed by this equivalence relation and union them together, we get back S. Saying that a little bit more carefully, we can say let E be an equivalence relation on a set S, and then we have this equation, right, where the union of all the equivalence classes with respect to this relation E gives us back S. And what we're imagining here is we have S, our big set, and we have these various elements in it. And we've said we have an equivalence relation, and we talked about how that means that things are going to be either related or not, and so we have these classes that occur. Say these guys are in their own class. What we're imagining doing is taking one representative element from each of these equivalence classes, and we're defining this set X, which has all of these representatives in it. And we sort of skipped this part a little bit, but that's what this X in X means down here. We've taken one representative from each of these, and we're now writing the big union of the classes formed by all of these. So if you don't like this big union notation, you could just sort of write this out as like if we had X0, the equivalence class of that, union X1, union, X2, etc., right? That would sort of all add up. That's what this is trying to express here. If we imagine that we have X0, X1, X2, etc., all in X, and that those are these arbitrary elements. And notice it doesn't really matter which element we pick from the equivalence class, since they all are part of the same class, and so this class notation still gives us the whole class. Now my picture makes it look like this theorem is true, and it is true, but how do we know that it's always true? And what you want to think about is, well, what would be the case in which it's not true? It would not be true if there was some element in S that is not part of any equivalence class, and so it gets missed when we take the union of all of the equivalence classes. But we know that that's not possible because equivalence relations are reflexive. And so it follows directly from the fact that equivalence relation is reflexive, that everything has to be at least part of its own equivalence class. And that means that the union of all these is always going to have to give us back the whole set. We have two last theorems to do, and my hope is that if you're following along with the concepts pretty well, that these theorems don't tell you anything terribly surprising. They're just kind of more careful statements of things that you would already expect. The first of these theorems is that equivalence classes are always either equal to each other or disjoint, meaning if we're talking about two equivalence classes, they're either the same class or they have nothing in common at all. And we write this by saying the following three statements are equivalent. When we say x and y are related by the equivalence relation E, we're saying that's the same thing as saying that the equivalence class of x is equal to the equivalence class of y. And it's also the same thing as saying simply that the intersection of these two equivalence classes is not the empty set. It's not empty. In other words, they don't have nothing in common, to say it in a double negative, right? If they have anything in common at all, then they are the same equivalence class. That's what this theorem states. I'm not going to do a proof of this theorem, but intuitively it just follows from this property that we've established, which is that the properties of an equivalence relation are such that if anything gets related, it gets completely connected. I don't know if anyone still remembers this ancient horror movie called The Blob, right? Where there was this like monster that if it touched you, you sort of became part of it. That's how I think of equivalence relations, right? Anything that's sort of in the relation, it just becomes absorbed into this entire class. And the only way to sort of remain outside the class is not to be related to anything in it at all. So as a consequence of this, if x and y are not related by the relation E, then we can conclude that their equivalence classes are not the same. And furthermore, that their equivalence classes are completely disjoint, that the intersection of these two things is actually the empty set. These statements are all just negations of the statements above, right? This is a negation of the first statement. This is a negation of the second statement. So nothing really major new is being established here. We're just restating this. And a way of thinking of this in a sort of colloquial language is that there's no partial overlapping of equivalence classes. You're either all in or you're nothing in at all. There's nothing overlaps at all. If you add together these previous two theorems about equivalence classes, you get our final theorem about equivalence classes, which is equivalence classes partition a set. And what we've done here is we said that the union of equivalence classes, remember, makes up the whole set. So if we take the union, we get the set back. And we also said that there's no way for anything to ever overlap. And so what this means is, I've been drawing this kind of throughout, right? It means that any equivalence class gives us this sort of carving up of a set into these disjoint pieces where we have various elements. Sorry for the colors here, that looks a little bit sick, but those are supposed to be elements inside an equivalence class. So Kazam, I have magically replaced that diagram with something that I hope is a bit cleaned up and looks a little bit less like it requires medical attention. I just want to say what a partition is, right? These are supposed to represent partitions, and a partition is this subset of the total set in which there is no overlap between partitions and everything is contained in one partition, right? So in a way, we've sort of proven this by definition of what a partition is and the previous two theorems. Finally, I'll add that equivalence classes are quite useful, and this property of equivalence relations turns out to be very helpful for counting things and reasoning about the relationship between sets, all of things that we need in many areas of math and also in computer science. So that wraps up our section on equivalence classes and equivalence relations. It's certainly not everything that there is to say about them, but I think it's enough for our purposes to get us started in this class.